we just want to go through them and see. So our basic situation is we have disjoint sets that form a partition of our sample space, so A1 through AN. And then some event B that intersects some or all of the the sets that form the partition. So the law of total probability states that the probability of B, or you could call it the total probability of B, is just going to be sum over the number of sets in your partition of the probability of B given AI times the probability of AI. So the trick for this proof is just to create sort of a new set of sets, or a new set of events, I guess, where you're calling the intersections. Let's find like a fun color. Okay. Where you're calling the intersection of B with each AI a new set. We're going to call them C. So C1 would be this zone. C2 would be where B intersects A2, which is this zone, blah, 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 up to Cn, which is the intersection of B with AN. This, like, the whole proof hinges on this statement here. That because our set of events A were disjoint, we're able to just intuitively make sense A2 and something else, because A1 and A2 don't share any elements. So it sort of follows from the definition of intersection of sets. Probability, we can say that the probability of B then is just the same as the probability of the U. What we're allowed to say is that it's the sum of the probabilities of CI. That's what the third axiom of probability tells us. Okay, and so then all we do is we just apply the definition of conditional probability to these intersections. Okay, so we know that definition of conditional probability of B given A is equal to the probability of A and B divided by the probability of A. Okay, and so we can just simply rearrange that and write the probability of A and B is the probability of B given A times the probability of A. And so then we're simply substituting in this piece for each CI. Okay, so then we can write the sum probability of the CIs is just the sum of the probabilities of B given AI times the probability of AI. And that's what we were after. Okay, let's look at our Bayes theorem. AI times the probability of AI divided by the sum probability of B given AJ. Indexing in the denominator, I'm not entirely sure what the motivation is for that, but you know, if you were going to go through and compute this, this is just sort of a dummy able to say that this piece that we're starting with will give us this piece, probability of AI and intersect B over the probability of B. And then we just apply the definition of conditional probability again here in the numerator. Okay, we can write this, which allows us to get this term after we rearrange. And I mean, all you're doing is you write down the definition of conditional probability, you swing this probability of AI into the numerator, and we have something with which to replace the probability of AI intersect B. And that's really all there is to it. We just rewrite using the pieces that we want, and we are left with the all-important Bayes theorem. Okay, thank you.